Valve overlap is the amount of time the intake and exhaust valves are both open at once. Less overlap produces a smooth idle and more slow-speed torque, but poor high-speed performance because there's not enough time for complete scavenging to occur. More valve overlap allows better engine breathing at high speeds, but poor performance at low speeds, rough idling, and higher exhaust emissions. Engines with fixed valve timing can only operate most efficiently at one specific speed. Engines that can vary valve timing and/or valve lift can operate efficiently at a wider range of speeds and deliver better performance at high speeds with a flatter torque curve. There are two types of variable valve timing, or VVT: cam phasing and cam changing. Cam phasing VVT varies valve timing by shifting the phase angle of the camshaft. At high engine speeds, the inlet camshaft phasing can be rotated in advance to enable earlier intake, increasing the amount of valve overlap. This is controlled by the engine management system and actuated by hydraulic valve gears. Phasing change is either continuous or fixed. Continuous systems normally vary the phasing angle between 0 and 40 or more degrees according to engine load and speed requirements. Fixed phasing systems alter phasing by a specific angular value at a specific speed and load condition. Single overhead camshaft engines can use cam phasing. However, double overhead camshaft engines can receive greater benefit from phasing change VVT, as the intake and exhaust camshaft can be controlled separately. Some manufacturers choose to alter phasing on both intake and exhaust camshafts, but it's also common that only the inlet camshaft is phase controlled, with the exhaust camshaft fixed. Cam changing VVT uses different cam profiles to lift the valves depending on engine load and speed. One common system uses two rocker arms for normal operation on its two intake valves, with a third, higher profile rocker arm between the other two arms. At engine speeds above 5,000 to 6,000 rpm, the engine ECU activates an oil pressure controlled pin that locks the three rocker arms together. The center rocker arm follows a larger and more aggressive profile, transferring its movement to the intake valves, which now open further and for longer. When engine speeds fall below the threshold speed, oil pressure is removed from the pin and a spring deactivates the pin. The rocker arms are no longer locked together, and the valves are controlled by the less aggressive outer lobes. Cam changing VVT can also be used in a similar way to deactivate a second intake valve at low engine speeds, increasing the velocity and swirl of the air-fuel mixture as it enters the combustion chamber. Throttleless valve control engines do not use a throttle butterfly to control engine power. Instead, intake valve lift is controlled to between 0 and 10 mm, or 0.39 of an inch, by the engine management computer.